Hi everyone. So this is one of the questions a student had emailed me some time back. So a lot of you email me questions asking some doubts. I may not have time to get back immediately, but if the question is good, I'll try to get back. I'll try to make a video of it. So that's what I think I've replied to many of you. Okay, so I think this question was mailed to me a long time back. So today I was just going through my mail, searching for some other file, and I accidentally found this, and I thought, okay, I'll discuss this question. Okay, so please don't hesitate if you have any doubts. Just write me an email or message me on LinkedIn with a question, and I may not reply immediately because I may be occupied with some other work. But definitely, if the question is good, I'll definitely get back with an answer. I'll try to make a video on it. So this is an interesting question. In fact, at a later stage, I'll make a series of lectures on LDOs, low dropout regulators. So this circuit falls under that category of regulators called series regulators. Okay, so it's a very simple circuit, but it looks a bit slightly complicated when you introduce a capacitor. So the question asks you to find out the current M1 through this MOSFET under two conditions. The first condition is this capacitor C1 is not present. In the second condition, this capacitor C1 is present. Okay. Now, in both these cases, what they are doing in the circuit is that they are varying the supply voltage VDD. And the variation is shown here. Okay, the supply voltage is changing from 4 volt to 5 volt in a duration of 1 second. So the slope dV by dt is just 1 volt per second. Okay. And it's also given the UGB of the Opamp, the operational amplifier circuit, which is an ideal Opamp. The gain is infinity. And they have given, since the gain is infinity, even if you assume a finite bandwidth, the closed loop bandwidth is going to be infinity. So they have given that the bandwidth is much greater than 1 hertz. So what does that mean? Any input which is changing at a rate less than 1 hertz, at a rate around 1 hertz, can be treated like DC. Okay, so you can just analyze it without taking any reduction in gain or any capacitive effects. Okay, so that's what this statement means. It means that this input, it's all it's telling you is that this input, when I say input, the supply voltage is changing. That change will be perceived by the circuit as though it's a DC change. It's such a slowly varying change that the circuit will respond to it the way it would respond to a DC input. Okay, so this is what we need to analyze. So we are supposed to find out the current flowing through the device M1 under two conditions. In the first case, the cap is present, cap C1 is present. In the second case, the cap C1 is, the first case, cap C1 is not connected. The second case, the cap C1 is connected. So we'll just try to solve this. So what I'll do is, before we solve this, the way I'm going to solve this problem, I'll just reduce this problem and try to solve an equivalent problem, which is much simpler to understand. And finally, I'll come to the solution for this problem. The first case is very simple. When the capacitor is not connected, it's very simple. The second case, when the capacitor is connected, you have to use a bit of understanding of capacitors and how the current through a capacitor flows and all that, and also how negative feedback works. Okay, so you have to keep all that in mind and analyze it. So that's why I've broken down that problem or the solution into some smaller problems, and we will look at the solutions of those smaller problems and try to understand what happens when you connect the capacitance C1. Okay, so first case, we'll just see what happens in the circuit. So this circuit, as I said, it's a negative feedback circuit. So if you traverse the loop here, so the gain from, if I increase this node will increase, and this is a common source, PMOS common source amplifier. So this node will decrease. So if you see here, I've tried to increase this node, but the feedback tries to oppose any change. So it's a negative feedback circuit. So that is clear here. Now, the other condition given is that the amplifier's gain is infinity. Now, I told this point many times, and when we discuss negative feedback, is that the moment you have an amplifier with an infinite gain, the error or the input, the differential input, V plus minus V minus, will become zero. Because for you to get a finite output, the input has to be zero because the gain is infinity. So that condition will be enforced by negative feedback. First, we saw that there is negative feedback. And the second thing is that we are looking at, since the gain is infinity, the error has to be 0, and the error in this case is Vref minus V0. The output node here is V0, which is fed back. That has to be equal. So your V0 will exactly be equal to Vref, and that is enforced by negative feedback. In fact, when we talk about LDOs, I'll do a more detailed analysis, considering the Opamp's gain and all that. So right now, this suffices. This is sufficient to understand this problem. So both these node voltages are equal, so the output voltage comes exactly equal to Vref. So the current flowing through the resistor, I'm going to call it capitalized subscript R. That current is simply given by Vref upon R, because the voltage across the resistor is fixed. So the current across the resistor is also fixed. Now there is something interesting here. Since the voltage across the resistor is fixed, the current is also fixed. I can simply replace the resistor by a current source of value Vref by R. Okay, I can replace this current source resistor by a current source of value Vref by R. So now let's say I change my supply by delta V. I'm increasing the supply by delta V. Now remember, the loop gain of this amplifier is infinity. So which means it will force the plus and minus terminals to be exactly equal. So even though I've increased VDD by, say, some small voltage delta V, the output will still remain exactly equal to Vref. That is enforced by negative feedback. Okay, so since that is enforced by negative feedback, because A is infinity, the error has to be 0. So V0 will still continue to be equal to Vref. Now the question is, previously, let's assume delta V was 0. If delta V is 0, previously, when V0 was equal to Vref, since the current through the input of the op-amp is 0, the current through the MOSFET IM was exactly equal to IR, the current flowing through the resistor. Okay, the same current was flowing through this, so both the currents are same. So I can say IR equal to IM, which is equal to Vref by R. Now I'm increasing the source voltage by delta V volts. If I'm increasing the source voltage by delta V, we are seeing from the circuit topology that these two nodes, the V0 is, even though this whatever be the changes that might happen in the circuit, because this gain A is infinity and the circuit is in negative feedback, these two nodes will be enforced to be equal. So V0 will still continue to be remaining equal to Vref, even though the supply is increased by delta V. So even though I'm increasing supply by delta V, the output will still continue to be equal to Vref, which means your IR will remain the same. Now in this circuit, IR is exactly equal to IM. So the current flowing through this MOSFET is also remaining the same. So if the current through the MOSFET is remaining the same, we'll for the time being ignore channel length modulation. Then the only possibility is that the VGS is remaining the same. So which means if your current is remaining the same, the change in VGS, delta VGS is 0, which means the gate voltage is exactly equal to source voltage. I've changed the source voltage by delta V. Then the gate voltage also has to increase by the same amount. So this is enforced by negative feedback. Now this property is a very interesting property. When we discuss about low dropout regulators, this is called power supply rejection. Even though there is change in the power supply, there is no change in the load voltage, and the output voltage is still equal to Vref, and that is enforced by negative feedback. Okay, so this is an interesting property here. So what I've discussed right now is if I change the supply by delta V, there will be no change in the circuit. The current in the resistor will still be Vref by R, and the current flowing through the MOSFET will also be equal to Vref by R, and that directly follows from Kirchhoff's law, current law. Okay, the Kirchhoff's current law. Now in the question, it was given that the supply voltage is changing linearly. The supply voltage is changing linearly from 4 volts to 5 volt in a duration of 1 second. That is given in the question. Okay, and it is also given in the question that the op-amp's bandwidth UGB is much greater than 1 Hertz. Since its UGB is much greater than 1 Hertz, this is changing at the rate of 1 second. Okay, so as far as the circuit is concerned, this input will look like a DC input. So previously I just assumed delta V is like a DC change. So I can analyze the circuit in a similar way and say that even though I'm changing the source slowly, the negative feedback will still enforce V0 to be exactly equal to Vref. That is enforced by negative feedback. So therefore, the current through the resistor will still be equal to Vref by R. And because your current through the resistor IR is exactly equal to IM, the MOSFET current will also be equal to Vref by R. Okay? Since MOSFET's current is fixed, which means the delta VGS is 0, so which means VG equals Vs. So if your source voltage is changing, your gate voltage will also track. It will change exactly the same way. Okay, so this gate voltage here will exactly follow the source voltage. Okay, so if you plot the gate voltage, you will actually see that the gate voltage will also increase by the same amount. I mean, remember the delta VGS, I mean, let's assume the gate voltage is initially biased at some VGP. So it will rise from VGP to VGP plus 1 volt. So that will be the change that the gate voltage will go through. Okay, supply is changing from 4 to 5. Gate voltage will change it from its nominal bias voltage to nominal bias voltage plus 1 volts in a duration of 1 second. Okay, now this is an easy problem. So this is what was asked in the first part of the question. So your MOSFET's current will remain exactly the same even though your supply is changing. Okay, so this property is what we call power supply rejection. So even though there is change in the power supply, the circuit is rejecting any changes. It's behaving as though it's not even responding to those changes. Okay, it's a very useful property. When we talk about low dropout regulators, we will talk about that in much greater detail. Now, the next part of the question is what happens when I introduce a capacitor here? This is what we need to analyze. Okay, what happens when we introduce a capacitor? Will there be any change in the circuit? That's what we need to look at. Now, before we analyze that, I will analyze two simpler problems, which is much easier to understand. Then we will go back to that problem when we introduce a capacitor. Now, what I'm going to do here is that I'm going to connect a current source, from the supply to this output node. So let the current source value be I0. Now, if I connect this current source, again, negative feedback will ensure V0 is exactly equal to Vref. So IR, the current flowing through the resistor, is fixed. That is still Vref by R. Now, if I apply Kirchhoff's current law at this node, you will see that current will be equal to the resistor current IR here will be equal to IM plus I0. So now the current flowing through the MOSFET will actually be equal to Vref by R minus I0. Okay, since this current IR is fixed, if I'm injecting an extra current from the supply into the resistor, then the current in the MOSFET will decrease by the same amount. Now, how will that decrease happen? Your gate voltage, how is that change happening? So initially, when let's say suddenly we inject the current I0 in the circuit, that I0 will try to increase this node voltage because there is an excess current flowing into the output node voltage. So then the feedback kicks in and it starts acting on it. So eventually this condition has to be satisfied. V0 should be equal to Vref, which means, and also Kirchhoff's current law holds true, which means IR should be equal to IM plus I0, which means IM was initially Vref by R fully. The moment you connected I0, the value of IM decreases. So which means its VGS itself had decreased. Mod of VGS has decreased for this MOSFET. So what will happen is your gate voltage of this MOSFET will slightly increase so that the V source to gate voltage will decrease so that your IM will decrease. And that's taken care of by negative feedback. But the current through the MOSFET is now decreased by I0 units. Okay, I0 is the constant DC current. Your current through the MOSFET is decreased by that amount. Now, in the same way, I'm going to assume this I0 current is a pulsed current, meaning initially I'm going to call this current source as a time varying current I0 of t, which was initially 0. It reaches a peak value of I0, and then for 1 second later, it falls back to 0 again. Now, how will the circuit respond? Now, let's for the time being again consider this 1 second is a very large duration. when you compare it with the time constants of your circuit, right? So bandwidth UGB of this op-amp is much greater than 1 hertz. It means that the time constant, the speed with which the circuit responds, is generally given by 1 upon the UGB. It's going to respond much faster than 1 nanosecond. So as far as the circuit is concerned, I can still treat this input like a DC input. I mean, of course, there are some step changes here, okay? But since I have not considered any capacitors here, you can treat this circuit as a circuit with an infinite bandwidth. So you can assume that this circuit has an infinite bandwidth. So the circuit's response will also be instantaneous. So now we will analyze it in time domain. So what happens in time domain? Initially, IM was carrying a current of Vref by R because negative feedback is enforcing V0 to be equal to Vref. IM was carrying all that current initially. Now, I0 goes from 0 to, I0 of t rises from 0 to I0 suddenly. The instant your I0 increases, what will happen? That current will be injected into the resistor. So the voltage will increase, suddenly the feedback will kick in and this amplifier will respond to it. Now remember, since the loop gain of this amplifier, this amplifier's gain is infinity, the positive and negative terminals will be forced to be equal. That will still be forced to be equal because the op-amp is ideal, bandwidth is very high, they both will still be forced to be equal. So therefore, this current through the resistor will still remain as constant, that will be equal to Vref by R. Now, Vref by R will now be equal to current through the MOSFET plus I0 of t. Now, we know I0 of t, so therefore the current through the MOSFET is simply Vref by R minus I0 of t. So I have shown the three waveforms here. Shown in pink is the current I0 of t. So it reaches a peak value of I0. Shown in yellow, this is the current flowing through Vref by R. That is always constant. It is always it's always equal to Vref by R. So this current is simply equal to Vref by R. But if you look at the MOSFET's current, which is shown in green here, initially it's equal to Vref by R, but the moment I0 of t kicks in, it starts absorbing current. The current in the MOSFET decreases by I0. So it decreases and it remains at a lower value as long as I0 of t is non-zero. Okay, I0 of t is constant and it's equal to 0. And once I0 of t goes to 0, you have to again, feedback will kick in and change your gate voltage of this P MOSFET. Initially, when I0 was becoming equal to capital I0, your gate voltage would have increased so that the current in the MOSFET decreases. Now, when the current goes to 0, I0 of t becomes 0, again feedback will kick in. Once feedback kicks in, what will happen is that the gate voltage will come back to its initial value. It will decrease. Okay, so there was a positive change previously. Now there will be a negative change. Gate voltage will decrease and come back to its initial value when I0 of t was 0. When your IM was equal to Vref by R. So that's what happens in the circuit. The current in the MOSFET will decrease by I0 units. So that's what I've shown here. This is IM as a function of t. This is what happens when I connect a pulsed current source. Now, keeping this knowledge in mind, we will go back to the circuit and analyze it. So now we are back to the circuit. We are supposed to analyze what happens when this capacitor C1 is connected in the circuit. Now, we had already analyzed this circuit previously. If the capacitor C1 was not present, or I think it's C1 was not present, we saw that the gate voltage was also tracking. The gate voltage was initially at, say, some bias voltage called VGP. It was increasing to VGP plus 1 volt in a duration of 1 second. Okay. Now, if your gate voltage is changing and the other end of the capacitor is fixed at V0 equal to Vref, that is enforced by negative feedback with an infinite gain. Your amplifier's gain is infinity, so that's going to force the output to be exactly equal to Vref. So now if you look at the capacitor, one end of the capacitor is changing from, I'm sorry, this is not 4 to 5. This is actually changing from VGP to VGP plus 1 volt. Okay. Other end is fixed. So therefore, a current is set in the capacitor and the current is given by CdV by dt. So if you look at the current through the capacitor, that will simply be the derivative of the voltage across it. Vref is always fixed. So now the current will look like a pulse waveform. So since the voltage across the capacitor is changing this way, this is Vc of t, the change in the voltage will be 0 to 1 volt. Okay, VGP minus Vref, there is a DC voltage there. I'm ignoring the DC. I'm considering only the change in the capacitor voltage. Okay, let's call it delta Vc of t. So this is the change in the capacitor voltage. So the dV by dt is 1 volt per second. So the current through the capacitor is C into 1 volt, C1 into 1 volt. The value of capacitor is not given, but we can call this current as, say, capital I naught. So let's call it some fixed current whose value is equal to I naught. So now this problem reduces to the same problem which we had analyzed previously, which is a pulsed current source. What happens when I connect a pulsed current source? How will the circuit respond to it? The same thing will happen in this circuit also. In this circuit as well, your capacitor, whose one end was changing, is now going to behave like a pulsed current source. So for that duration, when the capacitor is on, it is supplying some current. So your IC of t plus Im should be equal to IR. IR is always fixed and it is exactly equal to Vref by R. That is fixed. But the current through the capacitor is changing. So therefore your MOSFET current will also change in response to that. So you will see the same waveforms which we had seen in the previous example. So your MOSFET's current, which is shown in green here, it will initially be Vref by R. It will decrease by a certain amount. And that amount is given by Vref by R minus I naught. Okay, and that I naught here is C dV by dt. And it is C1 times some fixed value. Okay, since C1 is not given, I'm calling it I naught. So the current decreases by that amount. And once the the supply signal goes back to 5 volts and remains constant, dV by dt becomes 0. So capacitor current becomes 0. So then the MOSFET's current will recover back to Vref by R. Okay, so if there are some time constants in the circuit, then the circuit will respond slightly differently. It won't respond instantaneously. It may have some kind of a first order RC response. Okay, depending on the system. If it's a two-pole system, it will be a second order response. Okay, so I'll talk more in detail. Right now, it's a very simple circuit. This is all, I believe, the person whoever has designed it would have thought of in this direction and wanted to see your understanding as to what happens when I introduce a capacitor. So it's mainly testing it. What it's essentially doing is adding a pulsed current source. Okay, so your MOSFET's current will decrease by that amount. Okay, so that amount is determined by the capacitor's current, and then it will recover back to its nominal value. Okay, that's it. So in case if you have any questions, please feel free either to message me or you can email me. Preferably, you can send a message on LinkedIn, and I'll definitely get back to you whenever I have time. Okay, but please don't expect an immediate response. Thank you.